There were people that had I don't think I really bad. And like maybe people also middle school. The English to oh.
All right, so let's go ahead and begin today.
Yeah.
So today, the big topic is multiplexer, also called a MUX, and it's part of your lab redesign. So, after the lecture and the activity today, you can start on lab 3, but you won't be able to finish it until next week. Okay, but like the previous labs, do some of it after the Thursday lecture. But again, you need more information on Tuesday to actually complete it. So, we're going to go over some basics of the multiplexer and then look at an example that's the gate level of a multiplexer, and then look at a timing diagram of a multiplexer, and then we're going to talk about how you would model a multiplexer in Verilog. Lots of multiplexer stuff. Now, before we get to the multiplexer, there's just 3 terms here that I just want to go over because these 3 terms in the digital world are used quite often. We'll use them in this class, the rest of this quarter. And then also, especially in CP 233, use this term. So first, there's this word byte with a Y. Does anyone know in the digital world what byte with a Y refers to? Right. Yeah, a byte in the digital world is 8 bits. Okay. How about the word word? The word word has a specific meaning in digital. Does anyone know? And this one's a little bit more, the definition isn't so solid as byte is, because byte is definitely 8 bits. Yeah, a word, the number of bits that a word represents actually depends. And it depends on how many bits are used to represent a certain piece of data. And usually the word length is the same as the number of bits that most of the registers inside a microprocessor can hold. Okay, so I put this structural diagram on every table. And this structural diagram, this is the microprocessor that you build in CPE 233, okay, follow on top. And if you look at this diagram, you'll see that many of the lines, right, that represent the connections between the different modules, it has a /32. What does that mean? 32 bits. So most of the data for this microprocessor that you build in CP233 is 32 bits. And that's because most of the registers, and we're going to talk about what a register is later on this quarter, but most of the registers that this microprocessor has can hold 32 bits. So we call this a 32-bit microprocessor. And the word length, the word length for the CPE 233 microprocessor, this is my shorthand for microprocessor, is 32 bits. Right? So we would say that that microprocessor has words of 32 bits. But if you had a 16-bit microprocessor, right, a microprocessor that most of the registers hold 16 bits, well, that would be a 16-bit microprocessor and the words would be 16 bits. Okay, so the amount of bits a word has depends. It's not like a clear-cut amount like a byte is. A byte is always 8 bits. What do you suppose a half word is? Yeah, just half the bits of the word. So yeah, it'd be 16 bits for CP233. But in general, it's just whatever number of bits you have for a word divided by 2. There's also this, old school term, if you will, that you don't hear about much. You don't hear about much anymore. And that's a nibble. Has anyone heard of a nibble in the digital sense? Can you guess how many bits it might be if a byte is 8 bits? Yeah, 4 bits, exactly. Good. Yeah, because a nibble is, you know, kind of like half a byte. You don't hear about this one much anymore, and that's because, you know, processing systems and microprocessors now have so many bits that, you know, 4 bits is kind of, you know, not as relevant. But back in the day, you know, back when I was an undergrad, it was right on the cusp of when, you know, 16-bit microprocessors were becoming kind of like state of the art. So most microprocessors were still 8-bit. This is like the mid-1980s. It was just on the cusp of going to 16-bit. So if you're dealing with a microprocessor that can only hold, you know, the registers can only hold 8 bits and your words are 8 bits, you know, 4 bits is, you know, rather significant. You know, so that's why back then a nibble, you would hear that term more. You don't hear about it, you know, much anymore. But anyway, just some ancient history, if you will. Ancient digital history. Okay, so anyway, those are what those terms are. Now, let's go over some basics of a multiplexer, also referred to as a MUX. Okay, this is the symbol of a multiplexer, and the multiplexer will have multiple what we call data inputs. So I labeled this one D0. And you can see I put all these dashes down to DN. And the reason I did that is because the data inputs can be any number if greater than 1. Okay, so you could have 2 data inputs, 3, 4, 5, 6, 7, 8, 9, you know, all the way up in theory to infinity. Okay, you can have as many data inputs as what you can fit. Okay, so you have multiple data inputs, but you always only have one output for a MUX. So for an output, a MUX output, there's always only one. Okay, so here I'm calling the output of the MUX F, as you can see. Okay, now the number of bits that the data inputs can have can be any number. So this is the number of data input bits. So it could be single bits like what I have here, right? Because I don't have a slash, or it could be 2 bits, 3 bits, 4 bits, 5 bits, 6 bits, 7 bits, 8 bits, let's say, you know, any number. And whatever number of bits the data inputs have, the output has the same number of bits. Okay, so if all my data inputs are 8-bit, my output would also be 8-bit, right? So the number of data input bits, you know, can be any. Okay. Now, there's another input. Okay, because like I said earlier, the MUX only has one output. So all these other are inputs. Okay, these are our data inputs. And then we have another input that's called select. Okay, this SEL stands for select. And the number of bits for the select input depends on the number of data inputs. So, now, I'll explain in a minute why it's like this, but if we only have 2 data inputs, then we only need a single selector. If we have 4 data inputs, then we need 2 select bits. If we have 8 data inputs, then we need 3 select bits. So do you see the relationship here? Right, that there's a power of 2, a whole number power of 2 relation between the number of data inputs and the number of bits that you need for the select. Okay, now I'll explain why that's so when we talk about how it functions, but that's the relationship. Okay. So the reason why we have this relationship I just talked about between the select and the data inputs is because a multiplexer functions like a multi-position switch. Probably the most common example of a multi-position switch is a dial, right? Like a hand dial, right? Like you might have, 6 or 7, things that you can choose with this dial. You just take your hand, manual dial, and you just turn the dial to, whatever setting that you want to choose. Okay. Well, that's basically how a MUX works, but it's electronic instead of manual. See, let's say I have a 4-to-1 MUX. And what 4-to-1 means is that there's one output, because there's always one output in MUX. But this 4 means that it has 4 data inputs. Label these inputs 0, 1, 2, 3. And I'll label the data D0, D1, D2, D3. Here's my select. Well, the select bits are going to determine which one of these multiple data inputs gets connected to the output. So if I want D0's data to be connected to the output, I have to put a binary 0 on this select. If I want data D1 to be at the output, I got to put a binary 1. If I want D2, I need to put a binary 2 on this. If I want D3, I got to put a binary 3 on this. Okay. So because I'm choosing between 4 things, that's why the select would be 2 bits, because it goes back to that relationship we talked about earlier in the quarter, that the number of values that you can get from a certain number of bits is equal to 2 to the number of bits. Okay. So if I had 8 data inputs, I would need 3 select bits, right? Because I need 3 bits in order to select from 8 things. Okay, does that make sense? So it's sort of like the select bits are acting like the hand, that turns the dial, that chooses which input's going to be chosen to be at the output. Okay. All right. So the next thing is a question for you, and that's looking at this diagram that's on the table. That's the structural diagram of the microprocessor that you build in CP233. Can you tell me how many muxes that microprocessor has? So how many times do you see a symbol like this? Yeah. 4? That's how many I counted. Yeah, I counted 4, because if you take a look, at this diagram, by this, where it says ALU, at one input of the ALU, there's a 4-to-1 mux. Up above that, there's a 2-to-1 mux. Then over here by this thing called the reg file. When you take this class, you're going to learn what all these things mean. But right above the reg file, there's another 4-to-1. And then over here by the PC, thing for program counter, this is a 6-to-1. Okay, so like I said, even though usually the number of inputs, data inputs, is a whole number power of 2, like 2, 4, 8, 16, it doesn't have to be. It can be any number. So this goes to show, because this mux here has 6 inputs. But if I have 6 inputs, what's the minimum number of bits that I need on my select? Yeah, it'd be 3, right? Because I couldn't use 2, right? If I have 6 data inputs and I had 2 select bits, I could only choose 4 of the 6, right? If I have 3, I can choose up to 8. Now I only have 6, but still 3 will cover it, right? It's just, this happens to have, 6 inputs instead of 8. Okay. So, one of the reasons I brought this diagram And if you could, don't take the diagram with me. If you want a hard copy, I can get you one. But I want to keep those for future classes. But the main reason I brought that diagram is just to show you that things that you're learning in this class are going to apply to when you take CP 230. Okay. All righty. So, any questions up to this point? Anything I've talked about that? You got the basic idea how MUX works. Now you're gonna do some practice, and it's gonna be part of lab 3. So if it's a little fuzzy still, hopefully, by next week, or hopefully even by the end of today's class, hopefully, you'll have a clear understanding of how it works. Okay, but the next thing I want to do is show you partially analyze the logic gate circuit of a MUX. Okay, so this is an example of a 4-to-1 MUX. Okay, again, 4-to-1 because the 1 refers to the single output. There's always just a single output for a MUX. And then the 4 responds to the 4 inputs that we have. Okay, so what I'm showing you here is I'm showing you the logic circuit that this symbol represents. Okay? Okay, so a review question. What kind of logic circuit is this? Is this NAND, NAND, NOR, NOR, SOP, or POS? Yeah, it's SOP, right? Sum of products is we have the AND gates giving us the products, right? And then the OR gate summing up. Okay, so yeah, sum of products. So a quick little review question. Okay, also you can see there's some inverters. Now, S0 and S1, okay, these are the select bits. So, in this picture, right, S0 and S1 are the 2 bits for the select input, right? And then as I said before, D0, D1, D2, D3, those are the data inputs, right? And that here is our output. All right, so now we're going to analyze this logic circuit, this logic gate circuit, and we're going to come up with what F would equal for the 4 possible combinations of select bits. And we'll do this top row, and I think after we do one of these, if I asked you to, I think you could do the rest of this. But if after I do this first one, you want to see another one, I'll do it. Okay, but we'll do this first one, and we'll see where we're at. Now, this is why I have the in-gate truth table, because we're going to need this truth table to do that analysis. So first of all, another review question. In an earlier class, we talked about universal gates. Is an AND gate a universal gate? No. There's only 2 logic gates that are universal. Which 2 are they? Right, the NAND and the NOR. And then what does universal mean here? Like when we say universal gate, what does that mean?
It can make any other gate.
Right, that you can use a NAND or a NOR to make any other gate, right? Remember that was a couple of classes ago and you had an activity? Well, on the board, I showed you how you can do a NOT, an AND, a NOR, and an OR with an AND, and then you did the same thing to the NOR in the activity, okay? So an AND is not a universal gate. Okay, in order to have a universal gate, it has to have an inversion, like the NAND and the NOR. Okay, also, when we were talking about universal gates, that was my first instance where, I said that it's important to understand a truth table, right? And, I think I might have said at that time that, a lot of times I'll talk to students about understanding a truth table, and they kind of look at me like, well, what's there to understand? You just look at the truth table, and there's zeros and ones, and you just see what inputs you have, and you get the output. What's that understand? Well, I gave an example of understanding a truth table when we were talking about universal gates, right? Where you look at half the truth table, and it will tell you something about the relation between the outputs and inputs, right? You look at the other half. Well, here's another example of that with understanding an AND gate truth table. See, if we split this truth table in half right here, and then you only look at the top 2 rows, right? You're only looking at the top 2 rows. Can you see what the top 2 rows are telling us? What's it telling us if one input's a 0? Yeah, if one input to an AND gate is 0, the output is 0. It doesn't matter what the other input is. And if this AND gate had more inputs, like if it had 3 inputs or 4 inputs, it would be the same thing. That if one input to an AND gate is a 0, the output is a 0, regardless what the other inputs are. You don't have to know what the other inputs to an AND gate are if one of them's 0. It's gonna make the output 0. Okay? All right, that's what the top 2 rows tell us. Can you see what the bottom rows, 2 bottom rows tell us? You see what it tells us if one input to a 2 input AND gate is a 1? We make one input to an AND gate a 1. How does the output relate to the other input? It's the same, right? See, if one input to an AND gate is a 1, the output is going to equal the other input, right? If the other input's a 0, you get a 0 out. The other input's a 1, you get a 1 out. Okay? So again, that's an example of what's meant by understanding a truth table, right? You can get insight into the gate by sometimes splitting up the truth table like that. And you're going to see, having that understanding is going to make it easier to do this analysis of this Mux logic gate circuit. Okay, so let's come over here, and we're going to find out what is the output F when S0 is 0 and S1 is. Okay, so now before we start the analysis, let me just point out that wherever you see lines crossing, feel like there's a cross there, lines crossing there, and so on. There's no connection there. Okay, if there was a connection, there'd be a dot. Now, in old school diagrams, right, if you look like in an old digital logic book, you're likely to see something like this, where there's like a little hump where there's an intersection, and that's just to emphasize there's no connection. Okay, but you very rarely see that in diagrams anymore. It's only like old diagrams. Okay, most new diagrams, again, if lines cross and there's no dot, there's no connection. All right, so what's this NOT gate going to do? All right, it's going to flip this S0 to a 1. So we'll have one here, and this inverter is going to do the same thing. So this one at the output of this NOT gate is going to be at this input of the AND gate, right? See how it's connected right to that input. Then also, if you follow this output down, it puts a 1 on that AND gate input. Okay, now there's a 0 here. It doesn't go through an inverter, so this 0 is going to come over here, and it's going to be on the input of this AND gate. So what's the output of this AND gate? 0, right? Because just like we talked about, if you have a 0 on one of the inputs of the AND gate, doesn't matter what the other inputs are, you're going to get a 0 out. So you see, this is going to be a 0. So by knowing that, see, we don't have to bother knowing what's on these other 2 inputs. Doesn't matter. Okay. All right. Then let's look at right here, S1. So like we said before, this 0 gets inverted to a 1 here. So that's going to put a 1 on this second input of this top AND gate. I mean, it's also going to put a 1 here, but we don't care because we already determined the output of that AND gate to 0. This 0 here is going to go to this middle input of this AND gate. So that's going to make the output of this AND gate a 0. And then also, this 0 goes to this input of this bottom AND gate, which means the output of this AND gate is going to be a 0. Okay, so the only AND gate left to determine the output of is this top one that has a 1 here, a 1 here, and then D0, okay, the data is at this input, and the data inputs could be a 0 or a 1. These data inputs could be either a 0 or a 1. Right? So you see you have these 2 inputs that are 1, and then you have this other input that's connected to the data that can be a 0 or a 1. So what is the output of this AND gate going to be?
1 or 0.
Well, when?
When D naught is 1, then it'd be 1 and that's 0, 0.
Yeah, exactly. Whatever D0 is going to determine what the output of that AND gate is, right? Because if D0 is a 0, you're going to get a 0 out. If D0 is a 1, you're going to get a 1 out. So you see at the output of this AND gate, we'll get D0, whatever that data is. Does that make sense? Okay, now at this OR gate, right, the outputs of the AND gates go to the inputs of the OR gate. So you'll have a 0 here, a 0 here, a 0 here, and then you're going to have D0 at that input of the OR gate. So what's the output F going to be? How does an OR gate work?
D0.
D0 again, right? Because remember how an OR gate works? You only get a 0 out of an OR gate when all the inputs are 0. Right? So when D0 is a 0, you get a 0 out. When D1 is a 1, you get a 1 out. So the output is just going to equal D0. Right? And that's what we said, right? When we were talking about how a multiplexer, a MUX works, we were saying, well, if the select is a 0, right? The data on input 0 is going to be at the output, right? So this shows that when the select is 0, output equals D0. Okay, and if you change the select bits to 0 and 1, you would see that the output is D1. If you change this to 1 and 0, you'd see it was D2. If you change it to 1, 1, you'd see it was D3. So you'd have to do like 3 more analysis, right? Like 3 separate ones, but it's the same idea. So, I mean, if this made sense to you, the other 3 rows you should be able to do if you were asked. I mean, does anyone want me to do another row or? Okay. If you want me to do one afterwards, I will. If you want me to do it individually. All right, but let me move the camera. Move the camera. Let's see, let's go over here. That should be good. Okay. All right, the next thing to look at is a timing diagram example involving a MUX. Now, the activity for you to do today involves timing diagrams. Okay, so if you understand what I do up here for this example, then I would think there's 3 of them on that handout. You should be able to handle those 3. All right, so this is a 4-to-1 MUX, right? Because there's 4 inputs, and again, there's always 1 output on a MUX. How many select bits are we going to need since there's 4 inputs? 2. See, a common mistake is that I'll get an answer of 3. And the mistake that most people make when they think there's 3 select bits is they look at the 8, the number of bits on each input, and they think, oh, they have to do the 2 to the number with the 8 instead of the 4. But remember, the number of select bits, it depends on the number of data inputs. It doesn't depend on how many bits you have for each data. Okay, whether there's 8-bit data or 16-bit data, or this could even be 32-bit data, like the MUXes that are in that microprocessor for CP233. No matter the number of bits, this would be 2 because there's 4 inputs, data inputs. Okay? All right, so here's a timing diagram, and you all have looked at timing diagrams, right? Because that's what you have to look at in Vivado to verify your designs are working. So remember, when you look at a timing diagram, T equal to 0 is over on the left, and as we go left to right, time's progressing. Okay, and here, every time the select inputs change, we have to evaluate what the output's going to be. Okay, so you see where these X's are, that's where a change is happening. Also notice there's new notation here that I don't think we've seen before, the 0x. See how it's 0x3, 0x1, 0x24, and so on? 0x just means that what follows is in hex. All right, so this is 03 hex, 01 hex, 00 hex, 024 hex, and so on. So, 0x takes the place of a subscript 16. You know, because remember back when we were doing number bases and number base conversion first day of class, we would say that, you know, if you had, you know, some hex number, like maybe you have hex 72. Well, this to distinguish that from, you know, some other base, we put a subscript 16, right? And that way we know for sure that's a 72 hex, not a 72 base 10 or some other base.
Wait, so for inputting in number in hex, we put OX.
Well, just in timing diagrams like this, instead of using a subscript to, you know, denote hex, they use this other symbology, just the 0x.
Oh, I thought you were saying that's like something we had to type. Then it's also very type.
Type where? Like,
That's what I thought you did explain.
no, it's just another way to denote something that's base 16.
Okay.
Yeah, and it's typically done in timing diagrams.
Okay.
Yeah, that's all.
Okay.
Okay. Okay, so let's look at the time interval. Okay, let's look at the time interval before this change in the select happens. So this time interval here where the select is 3, right? It's at x3. Okay, so that means we have a 3 on our select input. So if we have a 3 on our select input, what data is going to be at the output? Which one of those 4? Which one? AA, yeah, because see, AA is connected to input 3. So when the select input equals 3, it connects the data on that input to the output. Now, notice that over here, when I did this example, see, I had the inputs going 0, 1, 2, 3, right, top to bottom. Here in this example, I'm going 3, 2, 1, 0, top to bottom. I did that on purpose because I wanted you to know that it doesn't matter the order that the inputs are drawn, right? It just matters what this select input is equal to. That determines what input data gets connected to the output. Okay, because sometimes people will see this and they'll see a 3 and they'll count down 3. They think this is always 0, 1, 2, say GD. Again, these inputs can be arranged in any order. I mean, usually they go in order, but sometimes it's descending, sometimes it's ascending. Usually not mixed up. Like you won't see like 2, 1, 3, 0, something like that. Okay. Okay, so the data on AA is going to be at the output, and at the time interval that the select is a 3, AA data is 24 hex. You see, that would just equal that data on AA. All right. So now let's see what the output would be during this interval of time. Okay, this interval of time when the select is a 1. That means now we have a binary 1, a 0, 1. So what data are we going to get if the select is a 1? Yes, CC. It's just going to be CC because that's the data connected to input 1. So CC is a 22 hex. 22 hex. And then right here it changes. See right here, CC changes from a 22 hex to an 83 hex. So it will change, that's the output of those. We have to put the 0x. Right here it will change to 83. Okay, and then we'll do one more. I'll do more if you want. But do one more, hopefully you get the idea. So during this time interval, the select is equal to a 0. So we have a 0, 0. So what data are we going to have at the output? DV, right? The data DV is connected to the 0 input. So we look at DV, and it's a 2A hex right here. So I shouldn't put a hex. So let's see, let me say again, 0, 0, DV. So it'd be a 2A hex here. And at this time, it changes to FF. Right, and then, during this time interval, right, when the select is a 1, it goes back to the CC data, and then during this time interval, when select is 2, the BB data would be at the output. Okay? So you see how it works like a multi-position switch, right? Because again, depending on what the select input is equal to, that's what's determining which one of these input data gets connected to the output. So we're selecting the input data with the select bits. The select bits are like your hand when you turn a dial to select something. Like an old TV, to see, a show or something. All right, so that's not a very good pattern. That should be. Okay, so any questions up to this point? Because again, the activity today is 3 timing diagrams where, you have to do something similar to this. All righty, so let's see. Next thing. Okay, the next thing is I want to show you how we want you to model the MUX that's going to be part of Lab 3. And I'm going to use a different device called a comparator as an example, okay? So here's where you're going to be doing something quite different in Verilog. Because up until this point, when you've modeled anything in Verilog, like, Lab 0, you did that 3-gate circuit. The 3 gates? Yeah, it was 3 gates. And you use the Boolean expression, right, with the assign. And then when you did the lockbox in Lab 1, again, you did Boolean expressions. And then for the most recent lab, the RCA, you did Boolean expressions for the half adder and the full adder. And then you use the structural model to connect them all together. Okay, well, starting this class, we're going to start using the power of Vivado, okay, the power of System Verilog. We're going to let the software do the work and essentially do the equations and come up with the logic circuit. Because starting today, we're going to start using if statements. Okay, we'll learn if statements today, and then Tuesday, we'll learn case statements. Okay, so just like in higher level languages, in System Verilog, you can do if statements and case statements. Okay. So this example has a common device called a comparator. Now, again, the comparator is not part of Lab 3. In fact, the comparator is not in any of the labs this quarter. Now, depending on what you choose to do as your final project at the end of the quarter, you may need a comparator, okay, depending on what you decide to do. So a comparator, is a very useful device. But my purpose of talking about it at this point is just to provide you an example of an if statement. So my hope is that seeing this example with the if statement with the comparator, you'll be able to come up with the if statement you need for the MUX for Lab 3. And this example for the comparator is much more, I won't say complicated, but just much more code than the code you need for the MUX. Okay, but I think it's better to show you something a little bit more than what you have to do than the reverse. Okay, all right, so like any module that you've been doing, you always start off with a name, right? So you can see here I call the comparator. Notice it has 2 inputs, A and B. Now, instead of putting a specific number of bits, I'm going to do very general here. I'm just going to say, a number of bits, so it can be any number. And then it's got 3 outputs, okay, and they're all single bit, GT, LT, EQ. So a comparator, as the name implies, the comparator, it compares 2 values, A and B, at the input, and then it either puts a 1 on GT, LT, or EQ. Can you guess what these stand for since it's comparing 2 values? Can you guess what GT, LT? Yeah, it's just greater than, less than, equal to. Okay. All right. So, like all the other modules that you've been doing, you got to start off after the name of the module. You got to start off declaring your inputs and outputs. So, you know, just like you've been doing, you would go input. And then because this is multiple bit, right, you'd have to put the top. Now, I'm putting number -1 because again, I'm being general, right? If this was 8, well, you'd put a 7 there, right? Because the 7 would be the number of the most significant bit. And then semicolon 0, right? Because we always have 0 for the least significant bit. And then you would have, you know, A, the name of your input, right? So that's nothing new. And, you know, you would do the same thing for B. I'm going to leave some gaps here because, you know, you already have seen this. But there's something different here, okay? There's something different for the out. And I'm going to just write some of it now and come back to it later. You would put output like you've been doing. And, you know, these are single bit outputs, so you don't need the bracket, square brackets with the numbers there. So we'd have like GT, LT, EQ. And then that would be the last thing we declare. So we put parentheses and then the semicolon. Now, I intentionally put a gap here between output and the names of the outputs because something has to go here. And I'm going to come back to it in just a little bit. Okay? All right. So the next thing is, and this is also new, is that when you have an if statement in System Verilog, you have to put it within what's called an always comb block. Okay, so after you declare your inputs and outputs, you're going to put always underscore comb. Okay, C-O-M-B. C-O-M-B is short for combinational. See, even though we haven't called the logic circuits that we've been working on thus far this quarter combinational, that's what they've been. And you have a combinational logic circuit when there's no memory. Okay, combinational logic circuits do not have the ability to store. Okay, they don't have memory. You're going to see in a couple of weeks, okay, right around the time of the midterm, so right around the end of this month, that's when we're going to start talking about logic circuits that have memory. And we call those circuits sequential. Okay, so combinational, no memory, sequential logic circuits have memory. Okay, in fact, the main part of a circuit that can store is called a latch, right? You know how I've been saying that if you get a warning in any of your designs thus far that that have the word latch in it, that you treat it like an error, and that's because we're doing combinational circuitry here. So if you're getting a warning that says you have a latch, that means somehow you made an error when now you have memory in a combinational circuit where you're not supposed to. And even though for basic designs, if you have an unintended latch, your design can still work. In CP233, that's not true. Like when you do this microprocessor, if you have unintended latches anywhere, it's not going to work. And that's because unintended latches introduce additional circuitry that can throw off the timing. And timing is really important in a microprocessor. Timing is not that important in the designs we do. Okay. And, when we get to memory, you'll learn about what a latch is and, it'll start making more and more sense the more you know about it. Okay, but getting back to this, and I just want to look at my notes here so I can limit the amount of syntax errors I make. But there's no guarantee that all the syntax is correct. My main purpose of showing you this is the format more so than the syntax, because you can figure out any syntax errors, right? All right, but the next thing you would put is you put a begin. Okay, and then we start the if statement. So we have if A greater than B. You need another begin. See, this begin is for the always home block. This begin is for this part of the if. Okay, so if A is greater than B, we're gonna set the outputs like this. We're gonna make the GT output equal to a 1, the LT output equal to a 0, the EQ output equal to a 0. Then you end that with a semicolon. Okay, then you need an N. Okay, this N goes with this begin. Okay, we're gonna need an N for this begin also, but that's gonna be later on. Okay, now, the if statements in System Verilog, you can have as many else ifs as you want, or you can have no else if, right? You could just have an if, then an else. Or you could have if, else if, else if, else if, else if, as many as you want, then an else. Okay, here we just need one else if. So the next thing would be else if A less than B. You need to begin again. Well, now we're going to set the outputs where GT equals 0, LT equals 1, EQ. And then we need an N for this begin. Okay, well, if it's not greater than, it's not less than, it's got to be equal to. So we would just have after that, let's see what I have. Else. And then you have it in, and then it would just be GT equal to 0, LT equal to 0, EQ equal to 1, and we need another N for this begin. Okay, so it's always good to keep track of your ends because you always have to match up begins and ends. So begin, end here, begin, end here, begin, end here, and then we need an end for this begin, right? We need to end the always cone. So you'd have another end, and then you'd have an end module. A common mistake is your begin and your ends don't match up. Like you either have, an extra end or you don't have enough ends. So you got to watch out for that. I always make that mistake. Okay. Now, getting back to this. Okay, remember I said we were going to come back to this, right? Anytime you have an output within an always cone like this, you have to put in between the word output and the names of the outputs that are within the always cone, you have to put logic. Okay, if you don't put logic there, you're going to get all kinds of weird errors. And again, you only have to do that when you have outputs or output, if it's singular, within an always cone, right? Because today, or before today, you didn't know anything about always cone and you weren't doing this, okay? So if you don't have an always cone, you don't have to do that. It's only when you have an always cone, okay? Okay, just point that out because sometimes people go crazy. Once I tell them this, they start putting it where they don't need it. You have a question?
So it will work even if right?
Say that again, please.
It will work even if you don't need it, right?
It will not work.
Like if I put logic and there's not an always cone, it will still work.
Oh, I see. If you put it where it's not needed. That's a good question. I don't think I've ever run across that. You could try it and see. I don't know. I've never tried it because I know not to do it.
Yeah.
But I mean, I don't think I've ever had a student come to me with that problem. And I don't doubt that maybe somebody did that in the past. So maybe it doesn't matter. You don't need it. So it would be extra if you did it.
Also, this is some Verilog error about paths.
No, it doesn't matter how much white space you have, but for readability, I would indent. Yeah, just for readability. I mean, I suppose you've been told that in other classes, right? That indentation is good just for readability. Yeah. So yeah, white space doesn't matter. Yeah, how much. Okay, there's another way to do this that I want to show you. Because you might like this other way better. Okay, the other way that I can do this is I can initialize my outputs first, okay, before the always cone. So to initialize output values, you would just put initial and then begin. And then you would just list your outputs with their initial values. So you can do GT0, let's say, LT equals 0, and EQ equals 0. And then you would end. Okay, so you see, all this is going to do is just initialize all your outputs to 0. Now, the reason you may want to do this in a case like this is because when you have multiple outputs, you have to do this begin end for each part of the if. If I just have a single output within my if structure, I don't have to put the begin end. And when I initialize all my values first, I only have to put the value that changes in my if. So by initializing, I can now do this. I can just, well, you still need the always column. So always underscore column, begin. But now I can say, you know, if A greater than B, GT equals 1. And then I can just go else if A less than B, LT equals else EQ equals 1. And then I can just end this and then end what? All right, so you see, when you have multiple outputs that are going to be within, you know, part of an if you just want to save some work, because, you know, this looks much more compact than this here, well, initialize your outputs first, and now you don't have to put the begin end because you're only putting the one output that changes. Okay, so, you know, which structure you use in a case like this is really personal preference. They'll both work. Okay. All right, we're at the top of the hour, but it should only take me about 10 minutes to finish. So unless there's a strong objection from somebody.
So
Do you object?
yeah, but the initial begin, is that replacing the output logic?
Oh, no. This other way is just from here down, like here. You still need all this because you still, if you do it this way, you still have to declare your inputs and outputs, and you would still need logic because, again, the outputs are within an always column.
Got it.
Yeah.
Okay.
Yeah, good question. Yeah, thanks. Yeah, I'm sure there's other people that was wondering that too. Okay, let me turn the camera. All right, so the lab 3, and notice in the agenda that we're doing part 2 of lab 3 first. So part 2 is today, part 1 will be on Tuesday, okay? So in part 2 of lab 3, we want you to model this mux. Okay, this is a 2-to-1, right? Because there's 2 data inputs, always 1 output. Then we got our select input. How many bits is this select input since we only have 2 data inputs to choose from? Yeah, it's just a single bit, right? So your select bit is a single bit. You can see here our data inputs are 4-bit, and also, of course, our output is 4-bit, because that always matches. The number of bits of the output is always matching the number of bits on our inputs for our mux. So we want you to use an if statement to model this mux. And as I said earlier, the if statement for this mux is much less code than what it is for the comparator. Okay, are you going to need an else if? No, because you only have 2 possibilities, right? This output is either going to be equal to A or it's going to be equal to B. And what determines whether the output is equal to A or equal to B? The value of select, right? So if select is this, output equals this, else output equals the other. It's a couple lines of code. Okay, I just want to emphasize that because my past sections, you know, I think some students think because I did this comparator example that it's gonna look like this, you know, so they start like writing all crazy kind of stuff. But again, I just did this as an example of the structure. And again, this is much simpler than that. Okay, it's just a if else. And the condition is the select, right? That's what determines whether the output's going to be the A data or the B data. Okay, so after you do the activity, what would be nice for you to complete before Tuesday of next week is, you know, create a new project. Hopefully you've been doing that for all the labs, right? You have like a lab 0 project, lab 1 project, lab 2 project. Now you're going to have a lab 3 project. And within that lab 3 project, you'll need a design source for the MUX that has the if statement. And again, the if statement goes within an always cone like we talked about. And then you'll need a sim file to test it out. How many test cases are you going to need to test this 2-to-1 MUX? 2. You only need 2 test cases. Right? You need a test case when select is 0 and make sure that your output's equaling A, and you need a test case when select is 1 to make sure your output is equaling B. Okay. And then the other thing you can do before Tuesday, because the lab 3 design also includes the RCA that you already designed. So you can just take the RCA design file and also the half adder design file and the full adder design file and just bring them into lab 3 project. Okay, you don't need to bring the sim files because you already simmed it, right? As long as you didn't make any changes to your half adder, full adder, or RCA design source, there's no reason to simulate the RCA in lab 3 because you already used it and you know it works.
So just need to move the 3 files. It doesn't need any other support.
Nope.
Infrastructure behind it. Just the 3 files.
Yeah, just the 3.sv files. You have your design source. Okay. Yeah, that's all you need. Yeah, you'll see that for the next several weeks, we're using you know, modules that you did the previous week. Yeah, so things kind of build, they're going to start building now. Okay. Now, just to give you a little preview of next week. Next week on Tuesday, we're going to talk about what a decoder is. And specifically, we're going to talk about a decoder that's called a 7-segment display decoder. Because lab 3, instead of having your output on LEDs, you're going to have your output on one of the 7-segment displays that's on your Basis 3 board. Okay, so we'll talk about a decoder, 7-segment display decoder specifically. You're going to build a 7-segment display decoder using System Verilog, and you're going to use a case statement for that. So we'll talk about how to do a case statement System Verilog on Tuesday, and then you'll sim that. Okay. So in lab 3, you're going to have an RCA, you're going to have a decoder, and you're going to have a MUX. And then you're going to connect them up in a certain way, and we give you the low-level structural diagram. So, you know, you're going to need another structural model like the RCA that connects up the lower levels together. And then when that circuit's all together as a whole, what it's going to do is it's going to add the 2 4-bit binary numbers, right? The RCA is going to add A and B just like it was in lab 2. But now we're going to show the results of that addition on a 7-segment display as a hex character. Okay, so that's where we're headed. Okay, but like I said, what you can do today is the MUX, and then on Tuesday you'll be able to do the decoder and also connect up the modules. Okay. All right. So, do you have any questions before you get started with the activity? You're all set. If questions come up, please ask. Okay.